So this is our last lecture in this topic. As I discussed yesterday, today I will also discuss some numerical question, except from the NCERT books, other question as well. And at the last of this class, at the last, I will give some brief overview of the overall course, overall chapter. Okay, so let me start. Let me start with the first question. It is said that one photoelectron, there is a one, consider a photoelectron which has the velocity is given, velocity is 2 into 10 to the power 7 meter second inverse, and also provided the mass of electron, which is already known to us. It is not necessary that always this mass will be provided in this numerical question. That's why I said in yesterday's class that we should remember some value which are oftenly used. Basically, one of that value is the mass of the electron, which is 9.1 into 10 to the power minus 31 kg. Okay, so if it, though they are provided in gram, that's not matter. We can convert. We can easily convert from gram to kg to any other unit. Now, what they have asked? They have asked the kinetic energy. So it's very much trivial question. Very trivial question. They ask the kinetic energy. What will be the kinetic energy? As we know, c square. So it will be half into 9.1, 10 to the power minus 31 kg, 2 into 10 to the power 7 per square. So it will be m square s to the power minus 2. So this unit will be joule. Kg, meter square, second to I second square. That means second to the power minus 2. This is the unit of joule as we discussed earlier. So 2 will cancel, and from here we can say that it will be 18.2 into 10 to the power minus 70 joule. Now they are asking in terms of electron volt. Then also we have to divided 1.6 into 10 to the power minus 19. This will be in electron volt. So if I do that, then it will be 18.2, 1.6 into 10 square electron volt. Okay, so if we do this numerical solution, what will be the value? Let's say if we use the calculator, 18.2 divided by 1.6 into 100. 1137.5 electron volt. Okay, so this is the kinetic energy. This is very much trivial question, but we also should solve this type of question as well. Okay, next question. Here is the next question. They asked for a monochromatic light. Any monochromatic light is there, and for that monochromatic light, when it is irradiated on the metal surface, they have provided the stopping potential, value of the stopping potential, which is, V0, that is 4 volt. They asked to calculate the maximum kinetic energy. So it's easy. They are asking the maximum kinetic energy. So how we can calculate that? We know that Kmax equals to half m Vmax square. What should it be? We know E V0. So let's put it. So Vmax will be 2 EV0 divided by m. So let me put 2. Here the mass of electron is not provided. Okay, but they are not asking the maximum velocity. They are asking the maximum kinetic energy. So they are asking K max. Sorry. It's very much easy then. They are asking K max. So K max will be this is EV0. So EV0 means E into 4 volt. V0 is given. So it is 4 electron volt. If we want to convert in joule, then we will multiply by 1.6 into 10 to the power minus 19. So it will be then 6.4 into 10 to the power minus 19 joule as well. We can write that. Okay. The third question. They said that the ratio of the two incident light is given. Stopping potential for for the light of different frequency, that is given. The stopping potential is given. Stopping potential is given. The ratio is given, which is 1:4 for different frequency. This is, let's say, new one. This is new two. These are the two different frequency. For these two different frequency, the ratio of the stopping potential is given. Let's say for the that means the stopping potential for the light of the frequency nu 1 divided by the stopping potential for the radiation nu 2 is 1:4. That is given. They ask that the ratio of the Kmax. So it's easy. It's very much easy. They ask the ratio of the Kmax ratio. So how we can find that? Kmax? No, not Kmax. They ask the Vmax. Okay. So as we discussed before, from here we can also write that the Vmax is proportional to root over V0. So easily we can write that Vmax proportional to root over V0, and stopping potential ratio is given, and it is in proportional root over, related to root over. So we can write then Vmax 1 divided by Vmax 2 is equal to root over V0 1 divided by V0 2. So what would be? V0 1 by V0 2 is given 1/4. So it will be 1/2. That means the ratio will be 1:2. Okay. Okay. Then let me solve more questions. First, they have asked here, there is a photon of wavelength. This is the wavelength given, and they have asked to calculate first the energy of the photon in electron volt, and they have also asked the momentum. We have to find out. Okay. The first energy should be h nu. That means hc by lambda. H is 6.626 10 to the power minus 34 joule second. C is 3 into 10 to the power 8 meter per second. And lambda is 4950 into 10 to the power minus 10 meter. Okay. So it will be 6.626 into 3 into 10 to the power 18, that means 16 joule. What was the value? 6.626 into 3 divided by 4950. Okay. So it is 0.00401 into 10 to the power minus 16. Now if you want to convert in joule electron volt, then this will be the value. So you can write 0.00401 into 10 to the power 3 divided by 1.6 electron volt. So it will be divided by 1.6 into 10 to the power 3 means 1000, 2.509. So it will be 2.509 electron volt. So this is the kinetic energy, not kinetic energy, sorry, the energy of the photon. Sorry. Now we have to evaluate the momentum. Momentum is, let's say, T. Then what we can write? So we can write that, yeah, from here also we can write lambda equals to h by P. So P equals to h by lambda. Okay. So now the h is, and lambda is, this is joule second meter. So the momentum will be 6.626 divided by 4950 into 10 to the power 24. So again it is 6.626 divided by 4950. It is 0.00133. 0.00133 divided by into 24. Okay. But what will be the unit? It is joule second. Joules means kg meter square. Here is the meter. So now it will be the meter cancelled. So it will be. So it is obviously the momentum. Mass into acceleration. It's correct. It's correct. So unit will be kg meters. It's Newton, right? No. 1 minute. 1 minute. Let me do this. Let me do this. So it will be joule second divided by meter, right? The unit part. Joule is kg meter square. Second to the power minus 2 second meter. So it will be kg meter second inverse. Okay. So this is mass and this is the velocity. Okay. So we can write this like kg into second. Yes. So it is Newton second. We can write in this form as well, but that is not required. We can write 1.33 into 10 to the power minus 27 kg meter second inverse. In this form, we can write. Okay. Actually, from here, we should calculate this. I think it's correct. Okay. So, now the fifth question, right? The power of the photon source is given, which is 25 watt. And the wavelength of that source, photon source, is 6000 Armstrong. And they have asked number of photon. It's easy. What will be the energy? E equal to hc by lambda. Okay. So, okay, you can write this. It is 6, then it will be 7. It is also in watt. Okay, so it will be 6.626 into 3 divided by 6 into 10 to the power 19 joule. 6.626 into 3 divided by 6. It is 3.313 electron volt or joule. So now the number of photon per unit second they have asked. So it will be power divided by, actually it should be the energy of radiation per second, because they have asked per second, otherwise there will be no per second, and all divided by energy of each photon. Okay, so this is power. Okay, so we can write this. What is given? 25 joule, and this is 3.313 into 10 to the power minus 19 joule. So it will be 25 divided by 3.313, 25 divided by 3.313, which is 7.546. 7.546 into 10 to the power 19. This is the number of photons. Okay. Good. Next, this was our fifth question. Let us do the sixth question. Sixth question is, they have given the wavelength of a UV ray that is given that lambda is equal to 5 centimeter. Then they have asked the energy of that photon. So in terms of EV, what will be the energy in electron volt? So it is very much trivial. I am not doing that. Using this formula, you can evaluate this. So I am not doing this question again and again. So next question is, okay, question number 7. The work function phi 0 for potassium, phi 0 potassium is given, which is 2.2 electron volt. Next, the threshold frequency they have asked. You have to evaluate the threshold frequency. Okay, so we know that h nu 0 is equal to phi 0. So nu 0 will be phi 0 by h. So phi 0 is 2.2 into 1.6 into 10 to the power minus 19 joule, and it is 6.626 into 10 to the power minus 34 joule second. So it will be 2.2 into 1.6 divided by 6.626. 2.2 into 1.6 divided by 6.626. It is 0.531. Is 0.531 into 10 to the power 15 second inverse. So we can write it 5.31 into 10 to the power 14 hertz. Okay, this is the threshold frequency. Okay, let me do the next question in different color. Question number 8. They have provided the wave function ratio for two different metal. For metal 1 and metal 2, the work function ratio is 1:2. For first metal, the threshold frequency is 6000 Armstrong. So they have asked that the threshold frequency for second metal. It's very much trivial question. I will not write anything because we know that phi 0 equal to h nu 0, which means phi 0 is proportional to nu 0. So it will be, from here we can easily write, it will be 12,000 Armstrong. Okay, they have, sorry, lambda 0 they have asked. Then only it will be the Armstrong, right? So this is, so it will be 3000. Clear? So phi 0 is proportional to 1 by lambda 0. From here we can write. Should I do explicitly? If we do, we can do easily. Explicitly also we can do now. Phi 0 1 equals to hc by lambda 0 1. Phi 0 2 is equal to hc by lambda 0 2. So from here we can write lambda 0 2 equals to lambda 0 1 into phi 0 1 divided by phi 0 2. From these two relations we can write, correct? So if we write, then it will be 6000 Armstrong into 1 by 2, because it is given 1:2. So it is 3000 Armstrong. Okay. 7 question. For zinc, the work function is 3.6 electron volt. For zinc, the work function is 3.6 electron volt. The threshold frequency is given CPS. Then they have asked the, okay, they have asked to evaluate the Planck constant. What is the Planck constant? Here they have asked, otherwise we know. For this type of question, we can verify our result. And also if we remember the value of Planck constant, we can easily put that also. That is not the correct way, but here we can find the Planck constant easily. Okay. CPS, what here one important thing is CPS. What is CPS? CPS means cycle per second. That means the hertz. And that means the second inverse. How? Let us understand. Let's say there is a 10 cycle per second. So 10 cycle CPS is there. 10 CPS. That means, what does it mean? It means that in 1 second in rotate 10 times. So that is the unit of hertz, right? Also the same thing. So CPS and hertz is the same unit. Don't be confused. So H will be phi 0 by nu 0, because we know this, right? If we put, then we'll obtain. So it is 3.6, 1.69, right? 3.6, 0.64. So you can write 6.4 into, so more or less close result, but it is exactly 6.626. Okay. The next question number 8. From a source, light is irradiated on the sodium metal, and the maximum kinetic energy of the emitted electron is 0.73 electron volt. Okay, the maximum kinetic energy Kmax is 0.73 electron volt. The work function of the sodium metal is also given, that is 1.82 electron volt. Then they have asked the energy of the irradiated photon on the metal surface in terms of electron volt. Okay, but this is the first question. They have asked the energy of irradiated light, and also they have asked the wavelength of the light. Okay, this is the question. Okay, it's also easy. Okay, first energy. How we can find that energy? We know that Kmax equals to h nu minus phi 0. H nu is the energy of the irradiated light, so we can write it as E. So we have to find the E. So E will be Kmax plus phi 0, because we know the energy of the irradiated light is used to kick out the electron. That is the phi 0. That energy is the work function phi 0, and the rest of the energy, the remaining amount of energy, is converted into the kinetic energy of that electron. So if we add the kinetic energy of the electron and the work function of the electron, the metal, actually then we can actually find out the energy of that electron. Okay, what will be that? Not electron, sorry, energy of the incident light, and that is, it's given, right? The Kmax is 0.73 plus 1.82 ev. So it will be 0.73, 1.82. 1.82 plus 0.73, it is 2.55. So it is 2.55 electron volt. Now lambda. It is again easy. Lambda, we know that E is equal to Hc by lambda. So lambda is Hc by E, 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8, all are in SI unit. So again we have to convert it into SI unit. So it will be 1.6 into 10 to the power minus 19, and it will be in meter. I'm not doing the same unit calculation again and again. We can easily do that. I have done it several times. So it is 6.626 into 3 divided by 2.55 into 1.6, and this is 34 into 8 minus 26, and here is 9. So this is 6.626 into 3 divided by 2.55, 1.6. 2.55, 1.6, 4.872. It is 4.872 into 10 to the power minus 7 meter. So it is 4872 angstrom. Okay. Because 1 angstrom equals to 10 to the power minus 10 meter. Next. Question number 9. For a metal plate, the radiation of the wavelength 5000 angstrom is irradiated and the maximum kinetic energy of that photoelectron is 0.3 electron volt. Then find out the work function of the metal in terms of electron volt unit. This is the question. This is very easy question. Let me find some difficult question. Okay. For a metal, in a metal surface, again the wavelength of the irradiated light is 4940 angstrom. The wavelength of the irradiated light is given, which is 4940 angstrom. The stopping potential V0 is 0.6 volt. Now, if we change the wavelength of the irradiated light, then the stopping potential is converted into that V0 prime, which is 1.1 volt. Then they have asked to find out the work function I0 and the wavelength of second radiation. Easy. The same kind of question. First, the stopping potential is given. This is the wavelength of the irradiated light. So here we have to find out the, okay, from stopping potential, we know that work function is equal to, or from here, K max is equal to energy minus stopping potential, right? And energy means Hc by lambda, the energy of the irradiated light. So K max means EV naught, Hc by lambda minus phi naught. We have to find the work function. So phi naught will be Hc by lambda divided by EV naught. So Hc by lambda is given. So Hc by lambda 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by what is the lambda 4940 into 10 to the power minus 10. It will be in joule actually, and it is minus what is the V0 0.6. So it is 0.6 into 1.6 into 10 to the power joule. So what will be the value? 6.626344940. 0.00402. And it is 18. 0.6 into 1.6. 0.96. So it is, we can write 4.02 0.96. So it is 4.02 minus 3.06 electron volt. Okay. If we don't need to convert electron volt. If we convert, then we have to divide this by 1.6, 1.19, 1.912, right? Okay. The second question is the wavelength of second radiation so that it is converted. Okay. So again we have used this formula. We will use this formula. V naught prime is equal to Hc lambda naught minus the work function. Work function is now known to us. We have to find this. So it will be, no, you also know this. So it is Hc by lambda prime is equal to EV naught, which is 1.1 electron volt if you multiply with electron minus, not minus, plus 1.912 electron volt. So it is actually 3.012 electron volt. So lambda prime will be 6.626 into 3 into 10 to the power minus, okay, 34 into 3 into 10 to the power 8, 3.012. Okay, 6.6263. 1.6, 3.012. 4.124. 34, 8, 26, 25 minus 7. So it is 4124 angstrom. Okay, question number 10. Okay, they have asked the temperature. Excellent question. Okay, they have asked the temperature, at which temperature the kinetic energy of the gas molecule is 6000 is equivalent to the energy of the photon of wavelength 6000 angstrom. Okay, then the which let me write the energy of gas molecule is equivalent to the energy of photon. This energy is actually the kinetic energy of 6000 angstrom. Okay, so we can write this kBT equals to Hc by lambda. So T is 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by kb. What is the value of kb? 1.38 into 10 to the power minus 23, and the lambda is 6000 into 10 to the power minus 10. Now unit. Okay, this unit is new to us. We did not find out this type of unit, right? What will be the unit? For H, it is joule second. For C, it is meter per second inverse. So it's meter for lambda. And so it is actually a joule. Here it is kb. What is the unit of kb? For kb, the unit is joule per Kelvin. So it is joule per Kelvin. So unit of Kelvin is appearing. The Kelvin is appearing, which is the unit of the temperature. So it is 6.34826 23. So we can write it 7. So it is 34, 8 is 26, and here it is. Okay. So 6.6263, 1.38. Okay, there is a 3 by 2. So there will be 2 by 3. Wait. 3 will cancel out. So it is 6.626 divided by 1.38 divided by 3. So 1.6004. So it is 16,000 almost Kelvin. So we can see that the energy of the photon for a red light, this is actually for the red light, is that much higher that if we want to make a gas molecule, we want to give the energy with the same energy in terms of kinetic energy of a gas molecule, then we have to increase the temperature up to 16,000 Kelvin. So it's terrible. Okay. Question number 10 it was. Next, question number 11. Okay. One electron and one photon both have the same de Broglie wavelength. Same de Broglie wavelength of value this. Then they have asked the ratio of the kinetic energy for electron and photon. Okay. Both have the same lambda. So for we know lambda is equal to h by p, and kinetic energy is p square by 2m. So p is root over 2mk. So h by root over 2mk. So both lambda are equal. So we can write that if both lambda are equal, then 2mek E should be equals to root over 2m photon, k photon. So we have to find the okay. No, not the kinetic. Sorry. For photon, there is no kinetic energy. I'm sorry. They asked the ratio of kinetic energy of electron divided by total energy of photon. This they have asked. Okay. So first, the kinetic energy of the electron, that we know lambda is equal to h by root over. Right. So this is the kinetic energy. So we can write that k is equal to h square by lambda square into 2m. Okay. And the total energy of photon, what will be the total energy of photon is equal to hc by lambda. So k by e they have asked. We can write lambda square, h square to lambda square. It will be reversed hc. So it will be h lambda m to lambda mc. Right. So it will be 6.626 10 to the power minus 34, 2 into 10 to the power minus 10. This is the mass of the electron, 9.1 into 10 to the minus 31, 3 into 10 to the power 8. If you want to check the unit of H is joule second. For lambda, the unit is meter. For mass of the electron, the unit is kg, and C is meter per second. So it is, this is joule. So joule cancel out. So this is dimensionless, and it should be because it's the ratio. So it is 6.626 divided by 2 into 6 into 9.1, and it is 34, 10, 24, 34, 24, 31, and 8, 23, and 24, 10 to the power minus 1. So it is 6.626 divided by 6 divided by 9.1 into 10 to the power minus 1. That means divided by 10 as well. It is 0.0121. It is 0.0121. So it is very, very less than 1. Okay, so this is the ratio. Let me do the last math. Okay, the 12th one. It's also easy. I'm finding but some difficult math. Okay, at one time, okay, this type of math we have already done. We will not do this same thing. All type of math we have already done. So nothing left. Okay. So the math part is already, numerical part is completed. So now we will focus on our exam Ghosh part. This is our last part of the entire discussion. Okay. First, we have to keep in mind that for photoelectron, as we started, for photoelectron, EV naught is equal to half m V max square is equal to K max, right? Second relation is phi naught, which is work function, equals to h nu naught. This is our work function. This is our threshold frequency. Okay. Third one. Third one is K max equals to E minus phi naught. Okay. Everything is known. K max we can find from here. And also the trivial one I forgot to mention, E equals to h nu is equal to, and also C is equal to nu lambda. These two are the basic equation. Okay. Next question. No, sorry, next equation. What we should remember that we have discussed. Yes, another one is lambda is equal to h by p. Okay. And for light, this equation we have to remember. This is m0 square. This is not, I did not discuss in class, but it's good to keep in mind. P square, C square. This is not that much important. This I just provided. This is just the energy of light in terms in using the relativity theory, according to the relativity theory, where the m0 is the rest mass and c is the speed of the light and p is the momentum. For light, what happens? For light, this is the general theory. For light, m0 is 0, there is no rest mass, so you will be p square, c square, that means pc. Okay. So these are the theory we discussed in class and is required for math. Okay, I think nothing left. And also, okay, and at last I'm just writing the important values. That is 1 electron volt is 1.6 into 10 to the power minus 19 joule. Value of H is 6.626 into 10 to the power minus 34 joules second. Third is mass of electron is 9.1 into 10 to the power minus 31 kg. Speed of the light is 3 into 10 to the power 8 meters per second. And nothing more is required, I think, and also the kb. Kb is 1.38 into 10 to the power minus 20. Kb is a Boltzmann constant. In joule per kg. Okay. So now let me stop the class. So we have discussed all the things, the theory part, the numerical part, the exam Ghosh part, all things we have discussed. So, okay, now entire course is completed. I hope you have enjoyed a lot and something you have also learned from this course. Okay, thank you.